Hi, I'm Hyeonjin from Korea University. This is a presentation for the paper Metropolis-Hastings Data Augmentation for Graph Neural Networks. Data augmentation is a common approach to improve the generalization ability of models in many domains. In image recognition, it is straightforward to identify operations that generate diverse samples while preserving the semantics, such as rotation, cropping, and small color jittering. However, due to the non-Euclidean nature of data space and dependencies between samples, designing effective augmentation on graphs is challenging. Recent works like Jinyoung generate augmented graphs via a differentiable edge predictor. ADA-Edge optimizes the graph topology based on the model prediction. And GraphMix presents interpolation-based regularization by jointly training a fully connected network and graph neural networks. However, they do not explicitly guarantee that augmentation has a proper strength and diversity. Here, we propose Metropolis-Hastings Data Augmentation that draws augmented graphs from a desired target distribution. We designed the target distribution to control the strength and diversity of augmentation. The strength of augmentation is measured by the change ratio of augmented ego graphs. Given the original graph G and the augmented graph G' with dropped edges and nodes, the change ratio of graph delta G is computed as shown in here. A K-hop ego graph is a subgraph of a whole graph at node Vi. It consists of neighbors within K-hops from node Vi and all edges between them. Since most existing GNNs with K-layers learn node representations based on their K-hop ego graphs, we measure the strength of augmentation by the ego graphs instead of the whole graph. To compute the change ratio of edges, we first assume that each node's message is initialized to a scalar value 1. And by simply propagating the node message k times, we can easily calculate the change ratio between the original graph and the augmented one. This propagation-based ego graph change ratio calculation can take the structural property of the graph into account. For instance, consider two different cases, dropping distance edges and dropping near edges. If we compute the change ratio in a propagation-based way, disconnecting edges close to the center node Vi causes a larger change ratio, which can be regarded as much stronger augmentation. It indicates that the amount of received messages depends on which edges are dropped as well as the number of removed edges. This structural property can only be handled from the ego graph perspective. Similarly, the change ratio with respect to nodes can be written as follows, with the mask vector m for the dropped nodes. In practice, this definition allows time and memory efficient implementation using matrix multiplications. And we define the diversity of augmentation as the variability of strength of augmentation. Then we assume that the change ratio of each ego graph delta Gi follows the Gaussian distribution given the desired variation, the mean for the strength, and the standard deviation for the diversity. Also, to have diverse graph change ratios, it is necessary to normalize the target distribution with the number of possible augmented graphs corresponding to the same change ratio. The probability for nodes can be formulated similarly. In sum, the overall target distribution is a joint distribution of dropped edges and dropped nodes. With this carefully designed target distribution, we need to obtain a sequence of augmented samples to train the model. However, direct sampling from this complex target distribution is difficult. To draw augmented graphs from this target distribution, we adopt Metropolis-Hastings algorithm. Metropolis-Hastings algorithm is a Markov chain Monte Carlo method to draw random samples from a target distribution when direct sampling is difficult. Given an arbitrary point Gt, the first observation in the sample, choose the proposal distribution Q which only depends on the current sample Gt. Draw candidate sample G' from the proposal distribution Q and evaluate the acceptance ratio A with the target distribution P and the proposal distribution Q. If the acceptance ratio is greater than or equal to the number generated from uniform distribution, then accept the candidate sample and set the candidate G' as the new current sample Gt. While repeating the sampling process, if the acceptance ratio is less than the generated uniform random number, reject the candidate, and sample another candidate from the proposal distribution until the candidate is accepted. By iteratively drawing candidates and evaluating acceptance ratio to decide whether to accept or reject the sample, the acceptance samples by Metropolis-Hastings algorithm follow the target distribution P. Sampling a candidate graph G' from the proposal distribution Q given a current sample Gt consists of 3 steps. In change ratio sampling, with the Gaussian distribution given the graph change ratio of current sample Gt as mean, we draw the change ratios delta G'(E) and delta G'(V) of our candidate graph. Then we generate G'(E) and G'(V) by applying the change ratio to the original graph G. For the dropped nodes, we simply replace the entire feature vector to zeros. Lastly, the augmented graph G' is constructed by merging 2 augmented graphs, G'(E) and G'(V). Given the current sample Gt, MH-Aug samples the candidate from this proposal distribution and decides whether to accept or reject the candidate. Inspired by recent works that show the importance of advanced augmentation method in leveraging unlabeled data, we adopt 2 regularizers. Consistency regularizer encourages the consistency of predictions on 2 consecutive augmented samples, Gt and Gt+1. An entropy regularizer penalizes unconfident predictions and sharpens predictions. The 2 regularizers can be applied to both labeled and unlabeled nodes in the node classification task. With these regularizers and the standard cross-entropy loss LS for labeled samples, the overall loss for semi-supervised learning is given as follows.
Hello, I am Seunghun and I will present about an analysis of our framework. This table shows the experimental results on node classification with 5 datasets compared to baseline models. Our framework MH-Aug with regularization consistently achieves the best performance in all datasets. MH-Aug without regularization, which is trained with only the cross-entropy loss on labeled data, also achieves improvement compared to the vanilla models. It also provides considerable gain on other base GNN models like GraphSage and JT. Lastly, we verify the convergence of MH-Aug with the synthetic and real data. We observe the behavior of MH-Aug with a simple toy example, a grid graph with 100 nodes. We only consider the changes of edges for simplicity. To visualize the results, we compute the marginal probability of edge being dropped. Edges with high drop probability is highlighted in blue. According to the proposed likelihood, the drop probability of each edge is determined by two factors: the number of nodes it affects and the influence on each node. If we set the strength of augmentation to high, edges on the outer side of the grid graph, which have more influence to their connected nodes, tend to be dropped, since the nodes around them have low degree. In contrast, if the augmentation goes weak, the probability of center edges is higher than others. To verify the convergence of augmentation, we plot the drop probability as shown in here. The red line indicates the drop probability of each edge, which corresponds to the lines on the grid graph. And these blue bars represent the distribution of augmented graphs generated by MH-Aug in practice. It shows MH-Aug generates augmented graphs following the target distribution. In addition, we show the efficiency of MH-Aug with a citation graph. This is a 3-hop ego graph of yellow node from the citation graph Cora. And this minimap represents the probability of edges, which is directly calculated by the marginalization of the target distribution P. Blue means a lower probability, and red means a higher probability to drop edges. In this case, we set the augmentation strength to be weak, so relatively unimportant edges likely to be dropped. We can also observe that the sample from MH-Aug tend to be drop edges, like that, have higher drop probability, which means MH-Aug can generate samples according to the target distribution. Due to the weak strength of the augmentation, little has changes compared to the original graph. Conversely, if the strength of augmentation is large, more important edges like edges acting as bridges between hub nodes tend to be dropped. The sample from MH-Aug shows a big difference compared to the original graph, since it drops important edges like this. Moreover, by adjusting the standard deviation in P, we can control the diversity of augmentation. If sigma increases, the edge drop probability of all edges becomes uniform. That is, MH-Aug subsumes random drop edge as a special case. We can see that the generated sample with high diversity has randomly dropped edges whether they are important or not. In sum, the ego graph perspective enables the explicit control of augmentation strength and diversity to make an advanced augmentation. In summary, we design a target distribution that flexibly controls the strength and diversity of augmentation. MH-Aug can draw augmented samples according to the desired target distribution. We proposed a simple and effective semi-supervised learning strategy leveraging sequentially generated samples from MH-Aug. We experimentally and theoretically verified that MH-Aug generates the augmented samples according to the desired target distribution. In future works, we are going to apply our framework to other domains, such as image, point cloud, and so on. Thank you for your attention.